No, it's like a theorem. Yeah, yeah. What's that? Power. We need to models. I'm a supermodel. Oh, that makes all better. Yeah, you guys, is it good? We're pretty good, right? Okay. Are you on better? Yeah. I'm going back to summer. Okay. The goats. Oh my goodness. Let's go. Let's go. Bro. Okay. Are you now? Crowded. Yeah, that's like I think the post right. I just jumped. That's one. Yeah. The real go. Jerusalem. Everybody's are real. You sign up for a talk. Yeah, standard time.
Well, standard time is 20 minutes. Like,
You know, anything that would have a day like it's already been lived like that. You're like, it doesn't matter.
yeah.
It doesn't matter.
Yeah. And then we go on this show like
Yeah. I'm sorry, I'm waiting for the talk to start. Yeah, Chris is like doing some random stuff.
how do you think like the analytics per minute for it?
You won't even I mean, it all depends on. Okay. Okay, we're starting. Hello, everybody. I'm Nicolas Coballe. I'm gonna be giving a talk on model theory, and my hope is that this talk is very accessible to a lot of people because the past couple of talks have been a little bit advanced. So I hope everyone will be able to understand what I'm talking about, and it's not too complicated. Okay, so model theory is a branch of logic that studies mathematical theories and their models. So logic has two main branches, syntax and semantics. So syntax would be stuff maybe you studied in like a philosophy course. So that'd be like proof theory. And semantics would be also something that you might have studied in a more advanced philosophy course, which would be model theory. So this is like the sort of outline of my talk. We're going to study what are languages and structures, what are terms, formulas, sentences, validities, and theories. What is a model? Very important thing. What is a proof? What is soundness and completeness? And what are some applications of model theory? Okay, so this talk might include a lot of definitions because there's a lot of things to go through. So just raise your hand and if you need to slow down and clarify anything. Okay, so definition, a language L is a triple FRC, where F is a set of function symbols, R is a set of relation symbols, and C is a set of constant symbols. Okay. And a L structure, M, is a quadruple M FRC, where M is a non-empty set called the domain. F is a set of functions, this from Mn to M, like M and F or to M for each F in F. So this F is different from like this F. This is curly F. This is like not a curly F, right? R is actually a set of relations on M for each R in R, and C is a set of constants C for each C and C. So languages are the syntax and L structures are the semantics. So let me clarify this is unclear. The languages are just comprised of formal symbols. They don't really like mean anything. They're strings. Whereas the L structure gives these strings meaning. Like they're basically interpretations of these strings. Is clear, Amy?
What's the function symbol?
So like curly F is just comprised of symbols for functions, whereas these Fs are actually functions. Jaren?
What is entity F?
This is just telling you for this F how many inputs there are, right?
So it takes n inputs?
N F inputs, yeah, for each, like this many, NF for, yeah. Joel?
Do you have a concrete example of languages and L structures and how?
Okay, so here's an example. So we'll first take the language of groups, and we'll just say it's the language with the binary function plus and a constant symbol E, which will represent the identity. So And a group structure, or like a L group structure, let's call them group structures for simplicity, is the set, we can say, for example, is a set the real numbers with the multiplication and the identity. So what we interpret as E will be the constant 1 in the real numbers, right? So the dollar is just multiplication, and this is 1. And it's important to note that M is a group structure, but M is not a group. Can anyone tell me why M is not a group?
I mean, we haven't like encoded any of the axioms like associativity or stuff like that, or inverses.
Yeah, exactly. So the real numbers with multiplication is not a group because 0 does not have an inverse, right? Okay.
What's the relations in the previous example?
There are no relations, but we can have as many relations as we want. Okay, so next is the definition. The set of L terms is a small set T, such that C is in T for each constant symbol, and each variable, like vi, so we have countably many variables, are in our set of terms, and for each like T1 to TNF, we have f of these terms. So the function applied to these terms is in as a term as well, right? So these are just like basically, for example, we have like constants are terms, variables are terms like v1, and then if we apply functions to these constants or functions to these variables, we also get a term, right? So we say phi is an atomic L formula. If phi, so I'm gonna say like use this this equivalence to be like it's quite literally this string. It's the string exactly, right? So phi is T1 equals T2 for terms T1 or T2, or phi is the relation of T1 to TNR for terms T1 TNR. Okay, and the set of L formulas is the smallest set W containing the atomic formula such that if phi is a term, then not phi is if phi is a formula, then not phi is a formula. And if phi and psi are both formulas, then their conjunction, their disjunction are also formulas. And then we can also, for quantifiers, if phi is a formula, then there exists some vi, so some variable, phi is a formula, and for all vi, phi is a formula. And we also say an L formula phi is an L sentence if it contains no free variables. Oh, Clark?
What is the difference between the set of function symbols and the set of relations?
So a set of function symbols is like, it's quite literally a function from your domain to like from n copies of your domain to your domain, right? Where a relation is just a subset of so like f will be from, so this is nf copies of m, whereas R will just be a subset of M and R, right? Make sense? Like example, like an equivalence relation would just be a subset of M squared, right? Because
Okay, sure, yeah.
make sense? And like you have like other relations like like non-equivalence relations, like if we have a set of people, then we can have like friends is a set of people squared, right? So like X is friends with Y or something like that. Yeah.
So like addition of like greater than.
Yeah, exactly. Greater than is a relation, addition is a function. There you go. Yeah.
By no free variables, do you mean that every variable should have like a quantifier?
Yeah, it's bound. All variables are bound. Yeah, that's exactly right. Okay, so this is a very lengthy thing, but it all basically says what should be intuitive. So if M is an L structure and phi is an L formula with free variables like this, and like V1 to VI1 to VIM, and A is actually like IM tuple of M, we'll define the relation. It's kind of hard. It's usually called models or V dash, and we'll do a induction on formulas. So if phi is quite literally the string T1 equals T2 for terms, then M satisfies or is valid for this for phi A if the interpretation of T1 A is quite literally equal to the interpretation of T2 A, right? And if phi is this relation symbol, then then this is valid in M if the relation symbol interpreted into M, into the model, is in the set of relations R, right? The interpreted relations. So, right, like these are just symbols, but once we actually give an interpretation to them, then this will actually be a subset of M to the NR. And we do this for if phi is equal to not psi, then phi is valid in M if psi is not valid in M, right? And we do this all for the rest of the things. We do this for conjunction. So conjunctions, obviously, if phi is psi theta, then it's satisfied if M if it's valid, if psi is valid in M and theta is valid in M. And then conjunctions is similar, but instead of and, we do or disjunction. And then for quantifiers, we obviously do it the same way, is that it's valid in M if there exists some B in M such that this is true, right? So we do it, everything we want, we expect to be true or expect to works, right? Like this is basically saying we're taking, what this thing is doing is we're taking some set of symbols and seeing if their interpretation in our model is actually true, right? Because the symbols, the syntax really have no meaning, but once we give it an interpretation in some model, right, then we can know if it's true or false, right? And we're going to commonly abbreviate implies for this and if and only if for this, right? We don't really need them as like formal like symbols. Does this all make sense to you guys? Does anyone have any questions?
I mean, could you just like summarize it by saying that it's an inductive construction of like all the sentences are true?
Yeah.
Okay.
Right? Like if I have some formula, then it doesn't really like make sense for that formula to be true if I don't give it some structure to be interpreted as. Like if like say I have the formula for all, like let's say I have the language of groups, and as I have like for all x there exists y such that x times y equals e, right? This is basically saying that everything has a right inverse. This doesn't make sense. Like this is just a string of symbols. But once I interpret this in maybe say the set z with plus and 0, then I can say if this is true or not, right? Where plus is like the normal addition and 0 is this is e, right?
Don't you have to have that one sentence like for all x exists y? Isn't that like an axiom in your language? Just like
we'll get to that. We'll get to that. Okay. So in L theory, T is a set of L sentences. That's it. And an L structure M is a model of an L theory T if each sentence in T is valid in that model. So when M is a model for T, we'll write it as like M models T like this. And we're gonna overload this this symbol a lot. I don't know why model theorists love this symbol and they love like this means a lot of different things, but contextually it all makes sense. So an L theory T is satisfiable if there exists an L structure M such that M models T. Otherwise, we say that T is unsatisfiable. And if T is an L theory and phi is an L sentence, then we say T entails phi if for every L structure M, such that M is a model for T, we have that phi is satisfied, or phi is valid in M, and we denote entailment again using this this V dash. Yeah, Raghav.
So entailment is basically like something implies the other thing, right?
So like basically entailment just means that if we have some theory and we have a model of that theory, then that like phi is entailed by that theory if every model of that theory has that phi is valid in that model. Yeah, Amy.
Can you re-explain what the L theory?
An L theory is just a set of L sentences. That's it. It's like it could be finite, it could be uncountable, it could be countable. Yeah.
Can every mathematical like structure, mathematical object be described as an L theory?
Not all of them, because some like mathematical theories like topology require like sort of second order characterizations. For now, we're going to stick to like first order characterizations.
Are you going to talk about characterizations?
Well, it's just a character like the way you define like topologies, you need to like have a sort of understanding of like subsets of a space. And in first order like logic, we can't really talk about subsets. We can only talk about elements.
Okay.
So that's what I mean by that.
So is the L theory just like the set of the axioms?
Yes, the L theory is basically the axioms.
Can you maybe give like examples of theories that are, I don't know, satisfiable or unsatisfiable, or some specific models of theories?
Yeah,
I
yeah.
had the exact same question as Josh.
Okay.
The line with the equal means for those of us who've never done logic.
So what?
What is line equal?
Which part?
Models.
This one?
Yeah, what does that symbol mean?
This is like a very overloaded symbol in model theory that could mean a lot. Sometimes it means like phi is valid in a model. Sometimes it means, so in this case, we just say this, like this it means entails. For when there's a theory and there's a sentence, it means entails.
What does it mean there? Line.
This one?
Yeah.
That means that M is a model of T.
Oh.
Okay, so now some examples. So should be more familiar. Yes, Rita.
Okay, you fixed it. Topology.
I have heard that there is some way to do first order topology, but I am not sure. I think, what's his name? Joshua Lau does something related to that. Peter Schultz commits, I don't know. I don't know if I don't know off the top of my head there's a way that we can do first order topology. But obviously from your conventional definition of topology requires you to quantify over subsets, which is not okay in first order logic. So let's let L group be the language of groups. Then the theory of groups, right, is given by these set of L sentences. So we have, obviously this is identity, and this is associativity, and this is inverses. So for example, let K be a field, and let our model be, or our L structure be GLNK with dot in the identity matrix. Then M is a model for the theory of groups, or we simply say that M is a group, right? This makes sense. This is the group of n by n invertible matrices. And yeah, this makes sense. We can just verify that, well, you can do it on your own time, verify that all these things are valid, valid in our model. Another example, the theory of rings. So we have a new language, or language of rings, which we have plus, subtraction, multiplication, 0, 1. And we just basically have the theory of groups plus all these other things that basically ensure that it's a ring, right?
Like on your previous slide, like do you not, as you say M is a group, but isn't M like the model for groups?
Yeah.
Isn't it kind of confusing to call it a group when the elements are groups? Or
What's the definition?
never mind.
I like, you can more precisely, M is a model of a group, but like obviously if it's a model of a group, it's quite literally a group. Yes, Joe.
So it's anytime you have like a mathematical structure, it's basically a model
of the theory of that structure.
Yeah, like you can have the axioms for a graph, which is just some binary relation given by edges, and if you have some structure that models the axioms of a graph, then it's a graph. Roughly speaking.
So the model is basically, so the model of a group, for example, is just the group, but without like operations or what is it? Like,
No, like this is a model for a group and it has these operations.
then what differentiates it from a group? Like, why do you say model?
Well, they're the same thing. They're basically the same thing.
Okay.
Precisely, it's a model for a group, but like it is a group. Like GLNK is a group with these.
Okay.
Yeah, Raghav.
And just as a follow-up to John's question, each structure has a unique model
Each
that induces it. So each group will have a unique model of the group that results in that.
Yeah. What do you mean by that? Unique?
Yeah.
No, they're definitely like multiple non-isomorphic groups that are models of groups. Right. And then we have a ring, and if we have the integers with the normal interpretation of plus, minus, multiplication 0, 1, and this is obviously a model for the theory of rings. So, Chris?
So in like model theory, you always assume like CFC or some sort of a.
Yeah, we don't want to talk about that too much because it's a bit messy. Yeah.
On that slide, can you use plus as times for the in class?
Yeah, like what this like well, what do you like the symbol really doesn't matter. Like the symbol you use for like plus or like multiplication or whatever, it doesn't really matter that much. It's just a syntax. Syntax is basically irrelevant. Okay, this is something more interesting. So let's our language be language of rings, and we want to do the theory of algebraically closed fields of characteristic P, right? So ACFP is given by the set of ring sentences. So all the axioms for the theory of rings, plus commutativity, plus multiplicative inverses, and then basically all the countably infinite sentences of the form for all a0, an, there exists x, such that this sum equals 0. So that just basically we're adding every single, like saying that every single polynomial has a solution, which is what we want for an algebraically closed field. And if p is greater than 0, we have this psi p, which is defined as for all x, the sum of x p times 0. And if p is equal to 0, we have the negation. We have all the countably infinite negation of all these sentences. So this is a bit more complicated than our theory of rings because we have an infinite amount of sentences in this, or infinite amount of axioms in this theory, right? And for example, if M is the algebraic closure of F3 with plus minus multiplication 0, 1 as usual, then this is a model for ACF3. Make sense? Okay, so now we're going to move on to what a proof is. So a proof of an L sentence phi, given an L theory T, is a finite sequence, so phi 1 to phi n, of L sentences where phi n, or psi n is phi, and for each I, psi I is in T, or sorry, this should be psi. Psi I follows from the previous ones by a rule of inference. So like modus ponens or like introduction or that kind of stuff. And then we denote this we say if phi can be obtained this way, then we say T proves phi. So some examples of first order proof systems include, if you've done any like logic courses, you'll like probably run into like natural deduction, secant calculus, Hilbert calculus, that kind of stuff. And all these things are basically the same. They can all prove the same amount of stuff. So it doesn't really matter which one you use. Does anyone have any questions? Is this clear? A proof is just a finite sequence of steps that you can all get by our rules of inference.
What are rules of inference?
I don't like stuff like examples like if you have like phi and you have psi, then you can get you can get phi and psi, right? Yeah, basic logic. Like if you have like phi implies psi, and then you have phi, then you can we can deduce psi, right? Like this is modus ponens, right? So these are like the rules of inference. So a proof system is sound if for every L theory T and every L sentence phi, T proves phi implies that T entails phi. So it follows just from induction on formulas that all relevant first order logic proof systems are sound. So this is basically saying that if you can prove something, then it's valid, right? Like if I have the theory of groups, if I have GRP, if I can prove something by, like let's say we can go back to this example. If I can, what's a non-trivial thing? Oh, like let's say if we can prove that in the theory of groups that the identity element is unique, then that means that in any group, any model of a group, the identity element is actually unique.
How can it be otherwise? How can it be otherwise? How can we, in a model of a theory, all the axioms are satisfied, therefore if we can infer something from the axioms, it should also be satisfied.
Yeah, that's exactly what we want, right? We want
How can this not automatically?
System might be proof. Like the proof system might be lets you deduce the stuff that are false.
Yeah, like a proof is purely syntactic. A proof is purely syntax. It's just a string of symbols that follow from the rules of inference. Only with soundness does this actually connect to something real, like the actual stuff they want to talk about. That make sense? And an L theory T is inconsistent if it proves like phi and not phi for some L sentence phi. Otherwise, we say that T is consistent. So this is a big theorem in logic and model theory. It's called Gödel's completeness theorem, and I will not prove it because it's very long and a bit boring. But it basically says let T be an L theory and phi an L sentence, then phi is valid in T if and only if T proves phi. So this is, most people have heard of Gödel's incompleteness theorem, but not a lot of people have heard of Gödel's completeness theorem, which I think is a much bigger deal. But basically what it's saying is that if you have like a theory and you have some sentence that is valid in every model of that theory, then there is a proof of that sentence, which is, I think, is pretty huge. So basically it's really saying if I have a sentence that is true in all groups, then I can find a proof of it. So corollary, if an L theory T is consistent, if and only if it is satisfiable. So we're going to let me prove this. Okay. So we're going to first assume T is not satisfiable. Then there are no models of T. And that means vacuously, for every structure M, such that M is a model of T, the sentence phi and not phi is valid in M. And by completeness, T proves phi. Right? And if we assume that T is inconsistent, then T proves phi and not phi. So if we assume if T had a model M, then by soundness, M, so this sentence would be valid in M. But by the way we defined validity, this is not possible. This is a contradiction, right? So that means that T has no models. And thus we've proven this. Okay. So this is a very important and deep theorem of model theory. It's called the compactness theorem. And we say an L theory is satisfiable if and only if every finite subset of T is satisfiable. So I'll also prove this. So the first direction is trivial because obviously if it's satisfiable, then every finite subset is satisfiable. So the other direction is assume T is not satisfiable. Right? So by above, that means that T is inconsistent. And so let sigma be a proof of and not phi. Because all proofs are finite, we only can make finitely many steps. Proofs are finite. Then we only need a finite set T naught from T, right? To prove this. So thus T naught finite is inconsistent. So it's not satisfiable. So yeah, that's the big thing about proofs is that they're finite. So that if we were to derive some contradiction, then we only need finitely many of the axioms of T to derive that contradiction. So that's the key point here. Make sense? So yeah, this is a different notion of completeness that we're going to define here. An L theory T is called complete if for any L sentence phi, either phi is entailed by T or not phi is entailed by T. This is different from our Gödel's completeness theorem that just gives us a duality between proofs and entailments, right? So here's some examples. So let's theorem of Z be the set of group sentences that are valid for the group the integers with plus and 0. Then the theory of Z is complete. So this is just basically every single if we make our this is every single sentence that is valid for the integers as a group. And obviously this is complete because either a sentence is true or not true for the integers. So another example, the theory of groups is incomplete. And does anyone know why? There's a very trivial way to show this. Well, there are a bunch of ways to show this, but I think it's very funny if you just show it this way. We have the sentence, there exists X, and then for all Y is equal to X. And then we have the sentence, there exists X, and there exists Y, and for all Z, we could call this phi1, this is phi2. X not equal to Y, and Y.
X is not equal to Y, but X is equal to
Sorry, X is not equal to Y, and Z is equal to X, or Z is equal to Y. So this basically says that this group only has one element, and this says this group only has two elements. Right? And obviously there are groups with one element and there are groups of two elements. So like if the theory of groups were complete, then this would be valid in every group, right? But this is not true, obviously. And its negation is not true. Like these are two sentences. Like phi1 and the negation of phi1 are obviously not entailed by a theory of groups. Like because we have groups that have one element, we have groups that don't have one element. Pretty trivial, right? This is pretty trivial. Yeah.
So when you say the theory of Z is complete, does that mean you literally cannot write a sentence in the language of groups that is not satisfied by theory of Z, or that its negation is not satisfied by theory of Z?
Sorry, what do you mean by that?
Because you said complete means either the theory entails the sentence or it entails its negation,
Yeah.
right? So that means any sentence you write with like any set of symbols that you write with the language of groups.
Every sentence will either be
and theory of Z would either entail that sentence or entail its negation.
Yeah.
And so you cannot write a sentence that doesn't satisfy this.
Yeah.
Okay.
So, and going back, see how so this is Gödel's incompleteness theorem, the theorem you're probably familiar with. And this says that first order Peano arithmetic is incomplete.
Given an L theory that's incomplete, is there a way to extend it in a way that it is complete? So like it's part of a superset, which is complete.
This is what we're basically doing here. We're just basically adding all the sentences that are true of Z, so that all models of this theory are basically isomorphic to the integers. That's what we're basically doing. It's kind of like a cheating way, but it's very hard to determine what are these sentences.
And by construction, this has to be unique.
Up to isomorphism, of course, yeah.
But for that example, you can't extend it to make it complete, right?
I mean, you
need to restrict it. Like you need to focus on a certain, like you did with the.
Yeah, I'm taking a specific model and just adding all the sentences that are valid in that model. Joel.
Isn't the theory of any sufficiently general algebraic structure incomplete? Like the theory of fields is incomplete because you can have fields with precisely two of
You should hold your tongue. Hold your tongue. Okay. Okay. So this definition: let kappa be an infinite cardinal and let T be an L theory with models of cardinality kappa. Then we could say T is kappa categorical if any two models of T of cardinality kappa are isomorphic. So this is a lemma. Let T be an L theory with infinite models. If kappa is an infinite cardinal with kappa greater than the cardinality of the language, then there is a model of cardinality kappa. I would prove this, but it kind of takes too much time. The idea is to basically extend our language with a bunch of constant symbols for each cardinal less than kappa. And then using finite satisfiability, we can basically interpret these constant symbols as individual objects in our structure. And because finite satisfiability only requires finitely many elements that are less than kappa, then this is possible for any infinite structure, like even countably infinite. And we just use the compactness theorem to show that there's one that exists of any cardinality. Yeah.
was a morphism of models.
Oh, so I did not give you a precise definition of model isomorphism. Basically, it is just a bijection on the underlying sets that preserve like all the sentences that are valid in one of them are also valid in the other. The best way to interpret it, if I have an isomorphism of group structures, or sorry, of group models, like models of groups, then they're literally group isomorphisms.
I'm asking morphisms. I'm asking
Well, it's not that important. You can just think of them in this case. You just think of them as your normal group homomorphisms and your like algebra homomorphisms, ring homomorphisms, that kind of. Yeah, Chris.
What's the cardinality of the?
Huh?
What's the cardinality?
What do you mean? What is a cardinality?
How do you define cardinality of like the L theory?
Like in our ZFC cardinality.
Yeah, but what's it measuring the size of?
Oh, it's the size of the underlying set, right? Like a model comes with a domain Z, so it's the cardinality of this.
No,
Sorry.
but you mean kappa less or equal to T or L?
Kappa is greater than or equal to the size of the language.
What's the size of the language?
If like, my Choco. Like we have a language of groups, which is equal to this. So this would be cardinality 2. Because we have one symbol and we have another symbol. Right? I mean, there's no reason we can't have an uncountable amount of symbols, though. We can have like, messed up stuff.
So the theory can make sense.
Huh?
So the theory can make sense.
Talking about the language. The language is just the symbols we can make sentences with. And theorem. So ACFP is kappa categorical for all uncountable cardinals kappa. So the theory of algebraically closed fields of characteristic P is kappa categorical. And this basically says proven just because some algebra fact, two algebraically closed fields are isomorphic if and only if they have the same characteristic and transcendence degree. And then an algebraically closed field of transcendence degree lambda. Okay, wait, how do I explain it? This is a bit complicated. But yeah. As cardinality is Aleph null. And if kappa is greater than Aleph null, then it has transcendence degree kappa. This is just some random algebra. Don't worry if this doesn't make any sense.
Did you think about
Yeah, just think about it, and it all makes sense.
exercise?
Exercise. Yeah.
So, okay, so it's not good if you have input by itself. If you place output code, but not separately closed.
I don't know. I don't know. Okay. So this is our important part. This is Bott's test. So let T be a satisfiable L theory with no finite models. Then there exists some infinite cardinal kappa greater than the cardinality of the language, such that T is kappa categorical. So then T is complete. So we're gonna prove this. Let T is satisfiable theory with no finite models. What is this? Sorry about that. Okay. First, we're gonna do suppose T is not complete. Then there exists sentence phi such that T is not entail phi and T does not entail not phi. Right? Thus, let T1 be equal to T union set phi, and T2 is equal to T union not phi, right? Because T does not imply this, or does not entail this or this, these things are satisfiable, thus they have models. And they also have infinite models. Now, by above, there is a way to make sure, by this lemma, there's a way to make sure that these models have cardinality at least kappa, right? So we make M1 be a model of T1 and M2 be a model of T2, both with cardinality kappa. And but by construction, M1 models T and M2 models T, but they are not isomorphic. And this is because they disagree about phi. If they were isomorphic, then they would agree about phi. But this contradicts kappa categoricalness.
So we can apply Watt's test to the theory of algebraically closed fields of characteristic P. So it's satisfiable because you have the closure, the algebraic closure of FP. There are no finite models because all algebraically closed fields are infinite. Like the theorem before says that the theory is like kappa categorical. So the theory of algebraically closed fields of characteristic P is complete.
Wow, that's crazy, isn't it? Oh, corollary. ACMP is complete.
Wait, Nick, is this what you meant when I said that I was wrong? Like
No, it's not what I meant. This is,
okay.
yeah, you're right. You're right. So then there's some applications. So this is some pretty powerful applications. Lefschet's principle. Let phi be ascendants in the language of rings. The following are equivalents. So if it's phi is valid in the complex numbers, it's also valid in every algebraically closed field of characteristic 0, which implies it's also valid in some algebraically closed field of characteristic 0, which also implies there are arbitrarily large primes P, such that phi is valid in some algebraically closed field of characteristic P. And the last one is that there is some M such that for all P greater than M, phi is valid in all algebraically closed field of characteristic P. And I think the culmination that I want to get to in this talk is Axe growth-indic theorem, which says that every injective polynomial mapping of Cn to Cn is surjective. This part is not too hard to prove with the above. So I'll just prove the Axe growth-indic theorem. So this is just a little application of our model theory to algebra, or so this is not complete abstract nonsense. Okay, there's some reason we do this kind of stuff. Okay, I didn't just talk about definitions for like an hour for no reason. Okay, so first we have to prove a claim. Oh well, first actually we'll define what a polynomial mapping is. So polynomial mapping f from, let's just say, Kn to Kn, where Kn is a field, is just a polynomial mapping such that f can be written in coordinate functions, f1 to fn, right? Where each fi is in k x1 to xn. So it's just coordinate wise, they're all polynomials. That's what a polynomial mapping is, right? So we have a claim. Every injective polynomial is surjective. So this is just the FPN with a bar over it. It's just the algebraic closure of FP with a finite field of characteristic P, or P elements. And the proof is just this. Suppose it isn't. Then let A bar be the coefficients of F, and let's B and be an element not in the range. Then we just take the subfields of FP generated by A and B. So take subfields. So notice that these are a finite set of elements. This is just the coefficients of A. There's a finite many coefficients. This is just one collection of elements in the range. So this is a B bar to mean like, because this is FP to the n, there's like n elements in the, right? And indices. And we just call this K, right? But then F restricts to a map from Kn to itself. That is injective but not surjective. But because FP closure is equal to the union of n equals 1 to infinity of Fp to the n, then any finitely generated subfield is going to be a finite field. But because this is finite and this is finite, every injective map from a finite set to a finite set is bijective. So this is impossible. This is a contradiction, right? Well, it's generated by B, which is on the range. This implies that this map would not be surjective, but it can be. Is that clear? Everyone following? So therefore, every injective polynomial mapping from Fp to the n to Fp to the n is surjective. And then the last part of the proof of actual Thindig is just that let phi and d be the formula that states that all injective polynomial mappings from Kn to Kn are surjective. With degree at most d, right? The reason we have to have this d is that if we want to have some sentence that includes like this that says this sentence in the language of rings that says this, we have to include some maximum degree just to make it a sentence. But we can do this, and it's a bit messy, but we can have a language sentence in language of rings that encodes basically what this is saying. And because FP closure proves phi nd by completeness, it ACF P entails phi nd, and then by Lefschetz principle, we have that so that's the whole thing. We basically reduce it to the finite field case, and we get it for free over C. That's yeah.
Are there any other proofs in math that use that type of like reasoning?
Like this reasoning exactly?
No, like this, like using what you were talking, like that an application of what we were talking about today.
Oh, I was gonna talk about it. So there's something called Ax-Shanuel theorem, which says that let F1 through Fn be power series that are Q linearly independent modulo C. Then the dimension of the transcendence degree of this field is greater than or equal to n plus the rank of this Jacobian matrix, where E is e to the 2 pi I x. I'm not going to prove this, but thankfully Jacob Zerman has a very nice exposition on his website about how you can apply model theory to this theorem. That's it. So any questions?
I think you don't need model theory.
Really? Really? It wasn't so nice. It's so easy. It was so easy.
I think you just like do like elimination theory, like you fix the finite extension.
Anyone else have any questions? Ruslan?
What is the relation between a theory in a certain language and monads on the category of sets? Because most of the examples you presented, like groups or whatever, there were algebras over let's say algebras over operands. Like groups is a group is an algebra of groups.
I don't know what an operand is.
Uh,
Okay. Done?
Since you can have any set of axioms and make these into like your L theory. We know that ZFC has axioms.
Yeah.
There's such a thing as like a model.
Yeah.
ZFC.
But it's a bit harder because then we need some growth into universe kind of stuff.
Can you give an example of a model of ZFC?
You can let him go.
Yeah, I was going to write that on my presentation, but I realized it's too much effort. But we can talk about it later.
Nick, we have like 5 minutes. Can we go over the model theoretic proofs that the continuum hypothesis is independent of ZFC?
Yeah, 5 minutes. I don't think it's possible. Anyone else? Anything else? Edgar?
Can you have a model of a model, and is there anything interesting if you study objects? Are there any model, like you have models of groups, and you go like 1 degree like higher a model of a model, and is there anything interesting?
That's too much. That's See, I want to avoid abstract nonsense as much as possible. That's a bit too nonsense. Okay, anyways, we have pizza.
So you guys are on math. We have 30 people and 4 boxes of pizza. So like I think, but I don't know how many slices per box. That's a problem. Okay, just make sure you save enough for everyone. Okay.
This was really cool. I enjoyed it.
You liked it, right?
Well, actually, like the first 40 minutes, I was like, because I didn't understand anything. But when you go to algebra, I was like, oh my god, this is so cool.
I'm saying you can do everything by reducing my pizza.
Yeah.
صحيح. ايه رأيك في اللي حصل في سوريا؟